Howdy. This video is on molecular shapes and polarity. Whether or not a molecule is polar or nonpolar depends on its shape. And if a molecule is polar or nonpolar can greatly affect its physical properties. It could affect its melting point, its boiling point, and its solubility. And so after watching this video, you should be able to determine if a molecule is polar or nonpolar. You should be able to determine if a bond is polar or nonpolar. And so we've talked about how elements tend to react by losing, sharing, or gaining electrons to get noble gas configuration. And so on one end, you have equal sharing of the bonding electrons. On the other end, you have a transfer of the electrons. Now we can tell where we're at on this continuum by looking at the difference in electronegativity. So electronegativity is a measure of the ability of an atom and a molecule to attract electrons to itself. The greater an atom's electronegativity, the greater its ability to attract electrons to itself. And so if you have a really big difference in electronegativity, that means one atom is much better at grabbing electrons to itself than the other, and you have a transfer of electrons and you form an ionic compound. If you have a very small difference in electronegativity, say less than 0.5, then you have equal sharing of the bonding electrons. Now, if you're somewhere between 0.5 and 2, you have unequal sharing of the bonding electrons, and you form what's referred to as polar covalent bonds. And so on this continuum, you can imagine going from right to left, you're increasing the covalent character of the bond. Going from left to right, you have increasing ionic character or increasing polar bonds.
An atom attempts to attract electrons toward itself when bonding with another atom. The level of attraction of each atom is called its electronegativity. When sodium and chlorine react, the chlorine atom removes sodium's valence electron and becomes a chloride ion. The less electronegative sodium atom cannot compete for electrons and becomes a sodium ion. The attraction between the ions is an ionic bond. When bonding atoms have nearly equal electronegativities, neither can attract electrons away from the other. In a carbon-sulfur bond, the electron pair is shared almost equally between the two atoms, resulting in a covalent bond. When hydrogen and oxygen react, the more electronegative oxygen atom cannot completely remove an electron from hydrogen. The shared electrons are attracted more to the oxygen than to the hydrogen atom. This unequal sharing is called a polar covalent bond. Polar bonds have a slightly negative and a slightly positive end.
And so if the difference in electronegativity between two atoms is between 2 and 4, we consider it's going to form an ionic compound. If the difference in electronegativity between two atoms is less than 0.5, we consider it nonpolar covalent. If the difference in electronegativity is between 0.5 and 2, then there's unequal sharing of the bonding electrons, and we consider the bond a polar covalent bond. Now you should remember your periodic trends as you go up and to the right. The strength of electrostatic attraction between the outer electron nucleus increases, electronegativity increases, electron affinity increases, and the size decreases. And so if we think about what a molecule actually looks like, it's kind of globular-like. In here, what we see is the surface, and the surface is one value of the electron density. And so this is for HCl. Now, if we put a charge on the surface, we can actually measure if it experiences a positive charge or a negative charge. And so the red indicates a negative charge, and the blue corresponds to a positive charge. So for HCl, the chlorine has a larger electronegativity, and so it's going to have the partial negative charge. The hydrogen is less electronegative, and so will have a partial positive charge. And so for a bond, if the difference in negativity is between 0.5 and 2, the bond is polar. Now for a diatomic molecule, diatomic just means a molecule with just two atoms. If the bond is polar, then the molecule is polar. Okay, that's only true for a diatomic molecule. And again, for a diatomic molecule, a molecule of two atoms, if the bond is polar, then the molecule is polar. And so we can look at H2. So you have two hydrogen atoms. The differences of electronegativity is 0, as that corresponds to nonpolar. For HF, the difference is 1.78, and so that would be a very polar molecule. So a diatomic with chlorine and bromine, difference is 0.2, and so that would be a nonpolar molecule.
Diatomic molecule, a polar bond must lead to a polar molecule. Consider hydrogen fluoride, shown here as the Lewis structure changes to a ball and stick model enclosed within the space-filling shape. Note the polar arrows and the colors. If red indicates high electron density and blue indicates low, you can see that the F end of the molecule is much more negative than the H end, and thus HF is highly polar. Between two electric plates with the field off, the molecules lie every which way. With the field on, however, they become oriented with their negative ends facing the positive plate and their positive ends facing the negative plate.
And so it's true that if you put a polar molecule in a field with an electric field, then the polar molecule will align. But the real importance about the polarity of a molecule is that it increases the attraction between the molecules. And so if you look at these two molecules here, the partial positive of one end is pointing at the partial negative of the other end. And so because these molecules are polar, it will have a stronger intermolecular force. And that's the real importance of polarity of molecules. But again, for diatomics, if the bond is polar, then the molecule is polar. For molecules with more than two atoms, it gets a little bit more complicated. And so we can look at CO2, and we can ask two questions. One, are the carbon-oxygen bonds in CO2 polar or nonpolar? And so if we look at the difference electronegativity, we have 3.5 and 2.5, and so that'd be a difference of 1. And so that means the carbon-oxygen bonds would be polar. Now the question is the CO2 molecule polar or nonpolar? And so even if you have polar bonds, you can have a nonpolar molecule or a polar molecule. And so you kind of have to know what the structure looks like. And so for CO2, this is what the structure looks like. It is nonpolar. The best way of thinking about a polar molecule is that one end has a partial positive charge and the other end has a partial negative charge. Now here we got oxygen on either end of the molecule, and so it's going to be nonpolar. Now one thing also to note is that whenever you have a center atom surrounded by the same type of outer atoms and there's no lone pairs in the center, it has to be nonpolar.
A molecule has more than two atoms, its shape can affect the polarity in a crucial way. For example, in carbon dioxide, since oxygen is more electronegative than carbon, each bond is highly polar. But the linear molecular shape makes the bond polarities cancel each other. So the CO2 molecule is nonpolar. Notice that the orientation of the molecules is random, whether the field is off or on.
And so again, it's putting it in the field, but the real importance is the interaction between the molecules. And so nonpolar molecules typically have a weaker interaction than polar molecules with each other. And again, to understand if a molecule is polar or nonpolar, we have to be able to visualize it. For CO2, you have a partial negative on one end, a partial negative on the other end. To have a polar molecule, one end has to be partial positive, the other one end has to be partial negative. And again, please remember, if you have a molecule with a center atom surrounded by the same type of outer atoms and there's no lone pairs in the center, that molecule has to be nonpolar. So CO2 is nonpolar, CF4 has to be nonpolar. And so looking at boron trifluoride, we could ask first the question, are the boron-fluorine bonds polar or nonpolar? And so if we look at the difference electronegativity, it's 2, and so those bonds would be polar. And now if we think about the shape, You have a center atom surrounded by the same type of outer atoms, no lone pairs on the center, and it tells us that that molecule has to be nonpolar. It doesn't have one end that's partial positive and the other end that's partial negative.
The case of boron trifluoride is similar to that of CO2. Because the three highly polar bonds point to the corners of an equilateral triangle, the bond polarities cancel each other, and BF3 is nonpolar. The molecules are oriented randomly with the field off or on.
And so again, we see that nonpolar molecules do not rearrange themselves in an electric field, but again, the real importance is the effect of intermolecular forces. And so again, whenever you have a center atom surrounded by the same type of outer atoms with no lone pairs in the center, the molecule has to be nonpolar, even if the bonds are polar. And so we can also ask the questions about water. So one is that hydrogen-oxygen bonds polar or nonpolar. And so hydrogen has electronegativity of 2.2, oxygen is 3.5, and so that would give us a difference of 1.3, and so that would be polar. Now the question is the molecule polar or nonpolar? And so you can imagine that oxygen is more electronegative, hydrogen is less electronegative, and so we'll have a partial negative on the oxygen, partial positive on the hydrogen. It should be polar.
The situation is very different for water. As in CO2, the highly electronegative oxygen pulls electron density towards itself, so each bond is polar. But the V shape of the molecule allows the bond polarities to reinforce each other, so water is highly polar, as the large polar arrow shows. With the field off, the molecules are oriented randomly, but with it on, their poles become oriented toward the oppositely charged plates.
And so we see it does arrange itself in an electric field, but again, the important part is how the molecules interact, and so you have a partial negative facing the partial positive of the other molecule. And again, this is a decent depiction of what a water molecule looks like. The surface corresponds to one value of electron density. The red indicates you have a partial negative charge, and the blue represents you have a partial positive charge. And so for ammonia, again, we can ask, are the bonds polar? Is the molecule polar? And so nitrogen's 3, hydrogen has an electronegativity of 2.2, and so that would be 0.8, and so that should be polar. And for the molecule, I have to think about the shape. And so again, we saw nitrogen's more electronegative, and so that would correspond to a partial negative charge here, partial positive charge there. You got 4 regions, and so that gives you tetrahedral electron geometry and trigonal pyramidal molecular shape.
BF3, ammonia has 4 atoms and 3 polar bonds, but the trigonal pyramidal shape means that the bond polarities reinforce each other. Thus, ammonia is highly polar for the same reason that water is.
And so again, the molecules would orient themselves in the electric field, and again, the importance would be interaction between the molecules would be stronger because the molecules are polar. Decent depiction of what a ammonia molecule looks like. Again, the surface is one value electron density. The red corresponds to a partial negative charge, the blue a partial positive. The bulge on top corresponds to that lone pair of electrons. Now for methane, you have carbon hydrogen, which would be difference electronegativity of looking at the wrong one, was 0.3, and so the carbon-hydrogen bonds are non-polar. The molecule, you have a center atom surrounded by the same type of outer atoms. The molecule also has to be non-polar. So methane, non-polar bonds, non-polar molecule. Now if we substitute one of the hydrogens of the fluorine, now we've got a polar bond. Fluorine is 4, carbon's 2.5, that gives you a difference of 1.5. And because you have the fluorine here with that partial negative charge, that will cause a partial positive on the hydrogen. And so this one would be polar. If we look at this one, we have fluorine on this side, hydrogen on this side. Again, fluoride is the most electronegative element. And so we'd imagine that this molecule would be polar. But it's interesting, you can have what's referred to as isomers, just different arrangement. And so we have exactly the same formula for these two molecules, 2 carbons, 2 chlorines, 2 hydrogens. But on this one, we have chlorines on on one side. This one, we have 1 chlorine here, 1 chlorine there. And so it's kind of interesting, even though we have exactly the same group of atoms, because they're arranged a little bit differently, the one on the left will be nonpolar, one on the right will be polar.
There are even cases when 2 molecules have similar shapes and identical compositions, but different polarities. Compounds such as cis and trans-dichloroethylene behave this way. Both have the formula C2H2Cl2, and both have trigonal planar shapes around the 2 carbon atoms. Yet, the trans compound is nonpolar because the carbon-chlorine bond polarities cancel each other, while the cis compound is highly polar because they reinforce each other. Since greater polarity leads to stronger attractions among the molecules, the cis compound boils over 18 degrees higher than the trans compound.
And again, whether or not a molecule is polar or nonpolar will affect its boiling point, melting point, solubility, and many other properties. And so notice that here, this molecule, because it's polar, has a little bit higher boiling point than this molecule that's nonpolar, even though they contain exactly the same set of atoms. And so we could ask the question, is xenon tetrafluoride polar or nonpolar? And whenever we ask that question, you're going to have to do a Lewis diagram. And so we're going to have xenon has 8 valence electrons, each fluorine has 7. 4 times 7 is 28, plus 8 gives us 36, so we have 36 electrons. And so if we think about the single bonds in the fluorine, that gives us 32, and then we add the other 2 on the xenon. Remember, elements in the third row and lower, like xenon, can have more than 8 valence electrons. Also notice that we calculated the formal charge, and the formal charge for all these atoms is 0. Now in terms of the electron geometry, that's just due to the number of regions of electron density. So we have 1, 2, 3, 4, 5, 6 regions of electron density, and so that means the electron geometry is octahedral. Now molecular shape is a little bit different. Remember, for octahedral, if you have 1 lone pair, the second lone pair always goes opposite the first. And so what you're left with is square planar. Now you might expect that the fluorine is going to have a partial negative charge because it is the most electronegative, but this molecule does not have one end that's partial positive and the other end that's partial negative. And so this molecule is going to be nonpolar. Now, molecular shape for this would correspond to square planar. Remember, electron geometry was octahedral. Molecular shape for this one square planar because the lone pairs go opposite of each other. So here we have phosphorus pentafluoride. Is that polar or nonpolar? That should be nonpolar. Remember, if you have a center atom surrounded by the same type of outer atoms with no lone pairs, has to be nonpolar. Here we have sulfur tetrafluoride. It's probably a little polar. You got a lone pair here. It's not completely symmetric, and so it's probably a little polar. For sulfur hexafluoride, center atoms surrounded by the same type of outer atoms, no lone pairs, has to be nonpolar. For this one, we got lone pair on one side. This is going to be seesaw shape, and it's probably a little bit polar. We could ask about the nitrate ion. Now, remember, you got 3 resonant structures. Each of these nitrogen oxygen bonds should be exactly equivalent, but it's symmetric. You have a center atom surrounded by the same type of atom, no lone pairs, and so it has to be nonpolar. And so these guys all have center atoms surrounded by the same type of atoms, no lone pairs. And so the top three have to be nonpolar. Remember, if you have a diatomic molecule, that just means a molecule with two atoms. If the bond is polar, the molecule is polar. And so HF is polar. Here you have boron hydrogen, boron fluorine. And so this is not symmetric, and so it's polar. Here the same thing. The carbon hydrogen is a nonpolar bond, but the carbon fluorine is going to be a polar bond. And so you will have a partial negative with the fluorine side and a partial positive with the hydrogen side. And so hopefully you remember that for diatomics, if the bond is polar, the molecule is polar. If you have more than two atoms in a molecule, it gets a little bit more complicated. But if you have a center atom surrounded by the same type of atoms with no lone pairs, then it has to be nonpolar. I hope that was helpful.